Hello everyone. In today's lecture, I'm going to present to you the method of variation of parameters for finding particular solutions of linear, non-homogeneous differential equations. This stuff is part of section 3.5 in the text. For comparison, I'll first briefly recall the method of undetermined coefficients that you are familiar with. Here in general, we are interested in solving differential equations like this with constant coefficients. On the right, we have a function that is in general different from zero, so this is a non-homogeneous differential equation. As we already know, the general solution of this equation is of this form: y equals yc plus yp, where yc is the complementary function, that is the general solution of the associated homogeneous equation. Yp is a particular solution of the non-homogeneous equation. If we know n linearly independent solutions of the homogeneous equation, then the complementary function is given by this formula. So the problem is to find a particular solution, yp, of the non-homogeneous equation 1. The method of undetermined coefficients asserts that if the right-hand side function f of x is of this form, then there is a particular solution of the non-homogeneous equation 1 that can be found in this form, where a naught, a1, and so on, am, b naught, b1, and so on, are unknown coefficients to be determined. Here there is a multiplier, x to the power s, where s is the least possible positive integer, such that neither of the terms that are involved in yp is a solution of the homogeneous equation. So neither of the terms right here is included in yc. Now the question is, how can we solve this problem if the function f of x is not of this form? And most functions are not of this form. And the answer is, we can use the method of variation of parameters. I'm going to describe this method in the case of a second-order differential equation like this. I'm going to note by Ly the left-hand side of the differential operator. Here p, q, and f are continuous functions on some interval I. They are given. I'll be assuming that we know two linearly independent solutions of the associated homogeneous equation. So therefore, the complementary function is given by this formula. And now the idea of the method of variation of parameters is to look for a solution, a particular solution of the non-homogeneous equation in this form. So the constant c1 in the complementary function is replaced by a function u1 of x, and the other constant is replaced by another function of x. Now, using the product rule, we can differentiate and find the first derivative of yp. Here is what we get. The terms here are slightly rearranged, but this is the first derivative of yp. The key idea of this method is to determine un and u2 so that this second term is identically equal to 0. So this is one condition on the derivatives of u1 and u2. Then yp prime takes this form. And now we differentiate once again. Using the product rule, we get this representation of yp double prime. Here again, the terms are slightly rearranged, but this is the second derivative. And now using the above representations of yp prime, and yp double prime, we obtain the following representation for Lyp. Right here is the second derivative of yp, here is the first derivative, and here is the function itself. Now it's easy to see that we can rearrange the terms of this representation so that Lyp is of this form. Now, here is a key observation. Since y1 and y2 are solutions of the homogeneous equation, then we have this equal to 0. This is also equal to 0, so therefore these two terms are equal to 0, and Lyp is simplified like this. Now the requirement that yp satisfy the non-homogeneous equation 4, that is this equation, implies that Lyp should be equal to f. So we have another equation that involves u1 prime and u2 prime. Putting these two equations together, we arrive at the following system for u1 prime and u2 prime. Observe that this is a linear system with determinant that is precisely the Wronskian of y1 and y2, which is always different from 0. So therefore this system has a unique solution. So we solve the system for u1 prime and u2 prime, then integrate, and we find u1 and u2, and then yp, a particular solution of the non-homogeneous equation, is given by this function. Now I'm going to summarize. This is what you have to know when you apply the method of variation of parameters. The problem is to find a particular solution of a non-homogeneous equation like this. The first step is to find two linearly independent solutions of the associated homogeneous equation. I'm assuming that we can do this. Then the idea of the method is that we can find a particular solution of this non-homogeneous equation of this form. And the derivation that I made a moment ago show that yp is going to be a particular solution of this equation if the derivatives of u1 and u2 satisfy these two equations. We consider this as a system, a linear system for u1 prime and u2 prime. It always has a unique solution, so we solve the system and then integrate to find u1 and u2. Then the desired particular solution of the non-homogeneous equation is given by this function. In every case, when we apply the method of variation of parameters, we have to solve a linear system like this. So I'm going to recall quickly how we solve linear systems like this in general. So here is a linear system, two linear equations in two unknowns, x1 and x2. The numbers a11, a12, and so on, b1, b2 are given. We know these numbers. I assume that the determinant of the system is different from 0, and then from what we did in class, we know that this system has a unique solution that is given by these two formulas. And this is everything for today. This is the first part of the lecture devoted to the method of variation of parameters. In the second part of the lecture, I'm going to demonstrate how this method works on two examples.